Thank you very much, Adrian, and thanks to Donald and Bernard for having me here today. It's a privilege to be at a celebration of this gentleman's life. Not only was he an amazing polymath in medicine, but he did a sharp line in moustache coiffuring, it seems to me. Anyway, I'm going to talk about translating genomics into patient care. And the reason that we're able to think about doing that today is because there was the Human Genome Mapping Project and the first sequence of a single person, which cost $2.7 billion. So we wouldn't be sequencing many more patients at that rate. And what you see here is a computer storage and computer system-based law called Moore's Law, but this has now been applied to sequencing, and you can now see that we're well below $800 per sequence, which means that it can be considered as something we would investigate for adoption in healthcare. Though you will not necessarily have thought about this, you're all billionaires, and you spend your billions in your form of the letters in your genome across the course of your life because it makes you the individual you are. Sometimes variation in that genetic code can carry susceptibility to disease, and there's a variation about every 300 letters. They can be single letter changes which might change an amino acid in a protein. It can be extra bits or missing bits, insertions or deletions, and then there can be bits of the genome that are copied, and all of these can carry susceptibility to disease. What our understanding of the early human genome map allowed us to do was to do large-scale genotyping using essentially a form of modified silicon chip technology where we genotype up to 1 million variants, and then we developed methods to impute from the 1 million variants because we knew where the rest of the variants were likely to be, and so we can now type in any one individual and impute about 9 million or so variants and therefore do genome-wide association studies. But the question is, can we really apply this for direct healthcare? And what are the benefits? And the vista on that was opened really by two major things. The advent of next generation sequencing. This is a most advanced form of sequencing, piloted initially just looking at 1% of your genome, which is the bit that codes for the proteins, but now extended through this program and others to whole genomes. So this is the setting for an unusual project, the 100,000 Genomes Project. And this is a section, a table from the as yet to be published National Genomic Strategy, which summarizes essentially the very large scale assets. Of course, the United Kingdom has a very strong heritage. We invented Sanger sequencing, we discovered the structure of DNA, and we invented next generation sequencing, and it was then bought, of course, by the Americans and sold back to us. And this, therefore, is, you missed that, you're a bit slow, aren't you? This is the architecture of the bit that I'm going to focus on, which is the relevance of all of this to direct healthcare. And so what we've used is the platform of the 100,000 Genomes Project and whole genome sequencing to make the argument for transformation of the entire NHS, not just whole genome sequencing, but also other tests, because it is the case today that there is a need for a mixed economy deployed to the care of patients. And then there are new initiatives under the industrial strategy, such as this 5 million healthy cohort led by John Bell in Oxford, where genotyping will be used to develop polygenic risk scores. In other words, measuring the aggregate of genotypes that might put you at risk of disease, and then calculating from your genetic makeup the likelihood that you have that disease, giving that information back to you, testing it in research to prove it's the right thing to do. And already we see over 3,000 publications from UK Biobank, although you'll notice in distinction to the other programs here, there is no feedback or very limited clinical feedback to patients. So it's against this backdrop that I take you back to London 2012. This is the Olympic opening ceremony. You'll have all worked that out. But this was an unusual Olympics in that David Cameron, the then Prime Minister, gathered scientists and also health ministers from across the world, and they advised him the moment was right for a free at point of care system to test the role of whole genomes in direct clinical care. And that gave birth to the 100,000 Genomes Project, which was announced in December 2012 in Cambridge. And then the Secretary of State for Health created Genomics England, a wholly owned Department of Health company. And we were created essentially to move with agility and speed, but actually you are our owners. All of the shares are held by the Secretary of State for Health on behalf of the United Kingdom taxpayer. And so we work within the health system, and we work with the health system to transform the application of genomics in direct care. The next Prime Minister after David Cameron opened the Sequencing Centre, and then the CMO published Generation Genome, her 2016 report, which I'll refer to again later. And now NHS England have commissioned new genomic lab hubs and a new genomic medicine service with a national test directory. And we reached the goal, in fact, on this very day last year of sequencing the 100,000th genome. And there's Dame Sally Davis, who's been a huge champion of this. Now, I suspect you're, like me, rather reluctant to show pictures of our politicians these days, but I am showing these guys because every one of these guys has been extraordinarily positively helpful. I'm not showing this because I want to influence your choice at election, because that's up to you. But I don't think I could let this moment go without saying each one of them, and I'm now on the third Prime Minister, who knows, it might be a fourth one on next week. I'm on my second Secretary of State for Health and my seventh Health Minister, and every single one of them has been rock solid behind this because they can see the potential. Now, the 100,000 Genomes Project is whole genome, so it's as much as you and I can read of your genetic code today. We can read about 98% of the genome. There's a little bit of the genome that's left over when we've read it, and the reason for that is because the technologies we have today read in short lengths, and they make it difficult to understand repetitive regions. It's difficult to know how to put them back together again. This reached over 97 patients from families with rare disease, patients with cancer, or people with infection, including we sequenced 3,000 TB organisms. We've now got over 21 petabytes of data. That's because an individual genome is large in storage size. You could only fit 2 or 3 on your laptop or your iPad, and you wouldn't be able to analyze them on that. Recognizing that there was substantial excellence in the NHS that had been under-resourced for many years, whereby people like this audience had been applying their own research resource to try and generate the findings for patients that they knew it was the right thing to do, we decided to persuade the NHS, and they did this, to commission genomic medicine centres. So to say, here's a recognition, this is a centre for excellence, and you serve this region. And part of that was about building out the legacy, because at the end of this, the baton has to return to the National Health Service for implementation. So what we tried to do is to build out capacity and capability by recognising excellence, investing it over the past 6 years, and then encouraging them to take this up and take it forward into healthcare. And they have done that. They've done the most outstanding job, and I cannot praise them enough. At about the peak of this project, about 5,000 NHS frontline staff touched this project at some point in their monthly work. And we've now assembled a coalition of over 3,000 researchers from 24 countries, because we don't know how to use all of this data so that we can optimize it for application in direct healthcare. So this is the project numbers as of today. So we have sequenced 118,000 whole genomes. That is in part because the NHS enrolled more people than we'd hoped, so a real tribute to them. But we were delighted with that because we've got more sequence, and we've returned 103,413 analyses to the NHS. That's about, you divide this in 2 for the cancer patients, it's just over 15,000 cancer patients who've been sequenced, and 72,000 plus people from families with rare disease. And 1 in 4, 1 in 5 people in the programme with rare disease with diagnostic unmet need are receiving a potentially actionable diagnosis for the first time. And 50% of the cancer cases may have a feature in their genome which allows them to access a trial or to receive a medicine in the NHS. This is the map of the programme, the architecture. So it was really, really important this was done by the NHS for the NHS, so there would be a legacy for the NHS. And so patient consent was taken in the genomic medicine centres. They supplied samples and clinical data, standardised, and also then we collect longitudinal life course data on every participant from every electronic health record we can get and every registry. And we assemble that into a very large clinical data repository. We have a sample repository, which is in Milton Keynes, and a sequencing centre, which is at the Sanger Centre. It's run by our partner, Illumina, and we did that because we wanted to put the person who owned the chemistry and the machines on point to deliver the project so that they would invest, and they did co-invest £78 million in it. We have our architecture, which I described, over 21 petabytes of data, and this coalition of scientists who will drive up the value, and then 130 plus companies that we're working with to try and extract health value from these data that will allow us to improve the lives of the most important people, the participants. And then once we've analysed the genome, we return a report to the clinician, and they own the relationship with the patient. Genomics England does not own the relationship with the patient. It must stay in the NHS, and they choose what is fed back to the patient and validate it and then relay it. So this is the journey of a genome in the project. Now, before I trigger this, there is no genome in our project that moves as fast as this one because it takes a while to analyse the genome. But we obtain DNA, here it goes, sequence it, annotate the variants that we find there, and then with the help of some companies, we tier those variants into most highly likely to be the cause of your disease, probably the cause of your disease, or this is in a gene which is likely to cause your disease, but we've never seen this variant before. And we return a report then to the NHS here, and simultaneously the data goes off for the researchers. This word GSIP is the Genomics England Clinical Interpretation Partnership, and we use the researchers to drive up the value and then return the findings where appropriate to clinical care. So I'll dwell on rare disease for a moment. Although rare diseases, there's over 7,000 of them, are actually rare. Because there are 7,000 plus of them, they affect about 5% of the UK population. That rises to 8 to 12% in the Middle East and parts of the Indian subcontinent. We allowed the NHS researchers from academic entities and also industry to nominate the disorders we worked on. There was one requisite. They had to have unmet diagnostic need. We standardized the eligibility and clinical characterization with data models that didn't exist, and we anchored all of that in an internationally accepted ontology, so that if you had done this in another country and there was only one family with a disease of this type in Britain, we could share data de-identified and understand what the architecture of that disease was and possibly get a diagnosis. We automated analytics, and the NHS own and confirm the gene panels and close the cases that we use to interrogate the genome. And here are the different disorders we're working across. Up here is the first family to receive a diagnosis, and I'll dwell on this for a moment or two. This young girl was 4 months old when she developed intellectual disability, fell behind her peers in milestones, and started to have intractable seizures, unresponsive to any antiepileptic. Mum and Dad had enrolled her in multiple other programs. No diagnosis had been found. We found that she had a defect in her sugar transporter that takes sugar from the bloodstream into the brain. This is called glucose transporter 1, and this defect meant that when her sugar dropped down in her brain, it triggered a seizure, and that explained why they didn't respond to the antiepileptics, because you weren't treating the cause. So we found this in her, but we also found something else, that this had occurred at conception in her, and these variants were not present in Mum and Dad. So Mum and Dad were never going to have other children, and now they are trying. And that's a big result for them because they thought they couldn't. So this is the familial wide implication. But let me take you on the journey of this child's genome. So this child had 6.4 million variants in her 3 billion letters. 677,000 plus were rare. 2,826 changed a protein. 67 were different from a mum and dad, and one of those was a clear cause of her disease. And we do this for the whole family in about 10 hours, going through the 3.3 billion letters. Obviously, we do multiple families in parallel, or we'd never have finished the project. There's one other thing to say about this little girl, and we do this for everybody in the program. We scour the worldwide literature to find out if there's even a single case report of something that's been tried that might have given benefit. So in this child's case, there is an established high-fat diet that you can give for this disorder. And she received that diet and has shown some improvement in her intellectual disability, but more importantly, her seizures have dampened down. And so that's a big thing for her. What if we could have found this shortly after birth? What would the trajectory have been? So I'll show you some other points from the program. So the other thing about the program is diagnostic yield up the side here was improved by increasing numbers of family members in the program, because you can use the genomes of other family members to filter out the variants that you're dealing with. That's how you get from 6.4 million down to 1. It's a tough thing to do, but this is hugely valuable. Another thing that was valuable, and we didn't know this for certain at the outset, was to collect deep clinical characterization of the patients. And at the outset, colleagues facing rare disease would say to me, you don't need all these clinical terms. You know, I can just with 3 things say you've got Caulfield syndrome. I don't need any more than that. And the point here was that, yes, you can say that I've got Caulfield syndrome, but you cannot tell me what the genomic cause of that is. And you've tried quite a lot of things, usually by this time, to try and unravel that. So if you give me more clinical data, it may be, and we won't know until we prove it, that it will cause us to allow us to achieve more diagnosis. So here's again the percentage diagnostic yield, and you can see across all, this is mirrored for all diseases, the more clinical data you give us, the better our chance of getting a diagnosis. So this has really helped. So here are some other things where we've applied this now in the NHS, because of course, as everybody knows here, and as Paul illustrated beautifully in his talk, you've got to have strong evidence of benefit before the NHS will adopt this in a cash-strapped environment. So the first child is a 4-month-old who had fluctuating neurology, repeated infections, was born, went straight to the neonatal intensive care and never left, and died at 4 months. And he died with no diagnosis. He'd had extensive immune testing, some genomic testing. Mum and Dad really wanted to know what this meant for future pregnancies, so we allowed children who had died to be enrolled by their parents in the program. And then Mum unexpectedly became pregnant and said, look, I don't want to know. Don't tell me the answer to this. I'm keeping this baby and I don't want to know. But at month 8 in her pregnancy, which is about 3 years ago, she became quite anxious and she said, actually, I really do want to know now. And we found that her deceased child had a mutation in a vitamin B12 transporter called transcobalamin 2. And in the literature, there were some case reports. And to be honest, we don't have, Paul was mentioning about real-world type uncontrolled evidence. Sometimes 4 or 5 people, so we really don't have randomized trials for these people. So it really is a case report situation. And there were case reports of high-dose vitamin B12 being given to some of these children once a week, and them actually having a different outcome. So the brother was born in February of 3 years ago and was tested by the NHS, and within 1 week they had discovered he was sadly also affected. But because of the case reports, they gave him high-dose weekly B12, and if he came in here now, you would after a little while notice that intellectually his thinking is not as fast as you might expect, but otherwise he's a laughing, happy child who's never been to the ITU. So this is a 10-year-old girl who'd had recurrent admissions to the ITU, and we've done the economics in this case, and she was at over £1 million of ITU stays. And she was admitted with life-threatening chickenpox, had had prior unusual infections with similar admissions, had detailed immune testing but no diagnosis. And she had mutations in her CTSP1 gene, which affects both B and T lymphocytes. And as a result of this, she was listed and had a curative bone marrow transplant. So if you look at her hospital episodes, you can see ITU, 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 bone marrow transplant, outpatients, 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 because she's only going now to be surveyed for a bone marrow transplant. Also, again, the familial wide, all her siblings were tested, and this turned out to be de novo in her. This next one is an interesting one, and you can see the video of this child on our website. This is a 5-year-old who'd had unexplained anemia, developmental delay, short stature and constipation, and had been given this diagnosis of Diamond-Blackfan anemia, which of course Adrian and others here who are connected to hematology will know is not a good thing to have, usually with a limited lifespan and high risk of cancer. But because of the developmental delay, we applied a panel to look at intellectual disability features and found that this child actually has thyroid hormone receptor alpha mutation, which is partly treatable by thyroid hormone. So this is an example, and we now have several of these in the program, where the clinical diagnosis is actually reprioritized and reassigned by looking at the genome. And the features were not unreasonable for the original diagnosis. It's just the genome unlocks the true diagnosis. So this is the words of one of the mothers in the program about her 5-year-old, and they want you to see her 5-year-old and know their names because they're very pleased with the outcome. This child had GAMP deficiency, and her mother thought that she was heading for a wheelchair and death, and she had uncontrollable epilepsy, nothing worked. She was really locked in and uncommunicative, and we found that she had GAMP deficiency, which is treatable with high doses of these simple things you've probably all eaten today. But for this child, this has been transformative. She no longer has seizures. Although she is not normal and she doesn't talk very much or say anything, she is now able to interact socially in a way she never was. And her mother is absolutely delighted with this. Now, I need to be honest with you, this is not the story for most of the people in the project, because although we have these stories of substantial change, for many, the diagnosis is the end of the journey. But the elation that this brings is disproportionate to the value in terms of prioritizing a treatment, because for many of these people there is no treatment. And the reason for that is the mums and dads who look after these people, or even the people affected, have often journeyed for a median of 5 years without a genomic diagnosis. And they know if you and I cannot explain the biology of the disease, we've got negligible chance of a treatment. And actually, most of the people in the program are not thinking about themselves. They're mostly thinking about someone else's children, someone else's loved one, and they don't actually expect the benefit for themselves. So it's great when this happens. I wanted to show you something that we've just been brought live in the NHS, and I didn't think we'd be able to do this. When you read the genome and the technology, you read in short lengths, so it makes finding repetitive regions that are over a long area of the genome difficult. So we've been using a form of machine learning, and this is a person enrolled with intellectual disability, and this is the Fragile X repeat. This is the normal distribution of Fragile X repeats across the population of whole genomes that we have. Here is the pre-mutation, which came from his mother, and here is his expanded mutation, which makes the diagnosis in this undiagnosed child of Fragile X. Here's another one. This is the Huntington's repeat locus. This is the distribution of the Huntington's repeat, and here's the repeat expansion. And this was someone enrolled with hereditary ataxia. In fact, I've just seen a very sad case where a child with hereditary ataxia we've found has, using this technology, exactly this expansion. And this expansion is present in his mum and dad as well, and neither of them have any features of Huntington's yet. But because you get repeat expansion and it continues to expand, the child is presented in childhood. So this is a very sad story, and sometimes it's like that, although there are now some treatments for Huntington's. So I'll just show you some of the diagnostic yields. Now, this is complex, but I just want you to focus on this bit here. So here are the percentage diagnostic yields by class. And what I want to highlight to you is certain disorders, neurological disorders, metabolic disorders, eye disorders, and intellectual disability were at between 40 and 50%. Bearing in mind these were people who were unable to achieve a diagnosis from routine care. So if I look at the first 5,000 cases reported on and look at diseases that fit with monogenic Mendelian disorders, it's about 34% diagnostic yield. And of course, we allowed people to enroll the other disorders where they thought there might be a genetic base, but they weren't sure whether it was a single gene or maybe a few genes. And of course, our diagnostic yield there is lower because we're dealing with a more complex architecture. But those will be hopefully resolved by research endeavor. Now, I wanted to explain to you, or share with you more, I should more correctly say, the diagnostic odyssey these people go on. So this is a 4-year-old who'd been to the hospital 151 times before her 4th birthday. I suspect none of us have done that here, but we looked at the cost of this in terms of the economics of this for the NHS. This cost almost £36,000. She saw all of these people, and we've been through this really forensically, not just internally with our clinical team at Genomics England, but also with clinicians from around the country. And pretty much everybody agrees that 20% of this was unnecessary. if we'd been able to get to a diagnosis. So the deployment earlier of a whole genome in this child's diagnostic odyssey would not only have brought her an answer, because we found the cause of her disease, but it would have avoided a lot of this. And one of the things that you see with these people in the hospital episodes, you know, I've children who've been 14 times to the hospital before they even get a genetic test. I've got children who've had the same test in 3 different hospitals over the course of about 6 or 8 weeks, because, of course, they're looked after in multiple centres. So we can release cash, and you can buy many genomes for 20% of that. So I'm going to turn now briefly to cancer. Cancer proved to be very, very tough, because the standard way we preserve cancer tissue, which is to take a biopsy or remove a tumour and drop it into formalin, is very damaging to DNA. And so what we had to do was to re-engineer molecular pathology, and I was grateful to the support of the College of Pathologists and others in producing a consensus statement, and we brought live 400 fresh tissue pathways across the NHS. So just to convince you why this was necessary, on the left here is the genome arranged in a circle. These connections here, these green lines, are structural connections between different parts of the genome. This is the same man's prostate cancer on the left and on the right. The difference between the left and the right is formalin. This is formalin. So many of these, you see where this looks like a child has scribbled on the genome, there's many of these are spurious structural connections. They're not real at all. You lose 17% of the AT letters from the genome. You have huge spurious excess of single nucleotide variants and insertions and deletions. So the product on the right is not good for clinical practice. The product on the left is what we need. Obviously, we've tried every way to optimize the one on the right. We do see that Paxgene, a fixative that's alcohol-based, produces an equivalent genome to this, but we could not make formalin work. So the overwhelming majority of these 15,000 plus patients with cancer in the program are fresh tissue. So we have the largest cancer whole genome resource in the world, and it's on the best quality platform of fresh tissue. Now, to my surprise, and this may change, although the data we have is compatible with other programs around the world, if you look in the blue and the light blue, you can see here that about 50% of the cancer patients, not uniformly across every cancer, could have actionable variants in a gene that's known to be associated with oncogenesis, that could be a driver to their cancer, might be a driver to response, might be a driver to relapse as well, or even adverse outcome. And this we found in about half the participants. And so what we did when we reported is not only did we tell you that you've got BRCA2 in your tumour and in your germline, we also told you, hyperlinked on this report, you could click on the report and just go straight to the trial where this patient could enroll. And then we also now are about to bring live in the NHS reporting of variants for pharmacogenomics. For example, DPYD is a particular gene where if it's got certain variants, you can have severe toxic reactions to 5-FU and capecitabine. So this is giving the oncologist a chance to avoid that toxicity, which you can't detect easily by other means. So here's bringing it back to single family as an example. This is a woman with breast cancer. She was not from an at-risk breast cancer community, and nor did she have a family history. But nonetheless, in her tumour and in her DNA that she'd inherited from her mum and dad, there was a pathogenic BRCA2 mutation. And as a result, she was able to enroll in the olaparib trial here called Olympia. And her daughter decided to have testing, and sadly is proven to be BRCA2 positive and has entered intensive breast screening with MRI and is considering other modes of treatment for that to avoid the risk of cancer. And the males in the family might be at increased risk of prostate cancer. So what I'm emphasizing to you here is there is a choice here, but there is familial-wide potential. And what if we can use some of this information where patients choose to use it to prevent or avoid a cancer? Because too often we're chasing cancer once it's advanced and we can't do as much as we'd like. Another way we've used these data is not simply to tell the clinician that your patient could be eligible for this trial, but to tell the trial investigator, for example, this trial is run by Tim Morn in Oxford, Focus 4 on Advanced Colorectal. We can tell Tim that Dr. X in Wessex has 20 patients who could be eligible. So he can approach Dr. X to say, I gather you've got 20 patients, and we say, Dr. X, you've got 20 patients for this trial, and here they all are. So this is what we hope to do in the next phase of our program, which is to greatly increase enrollment opportunities for patients into trials to get the latest and newest therapies and the best chance of effecting cure, or at least delay the disorder. Now, Paul, just for you, we're working with Public Health England and Derek Crook. We sequenced 3,000 multi-drug resistant TB organisms. And the interesting thing about this is a component of the Cryptic Consortium's paper in the New England Journal from September 2018, which we were involved in. 3,000 of those strains, and that's TB in the upper lobe. After Paul's talk, you won't need prompting on that. But the whole genome sequencing correctly predicted drug sensitivity. And once you actually have sequenced the organism, within a day you can tell what medicines they're likely to respond to. So now at the moment, as Paul said, PHE is sequencing about 1,000 organisms a month. And the other thing they're able to do is to track, using the TB organism's genome, the origin of the multi-drug resistance. And as Paul said, obviously most of it comes from Eastern Europe. So the other thing we've done is we looked at 6,000 genes. We've just finished 56,000. So we can find in the genome gene-drug interactions that are recommended for testing as part of the Clinical Pharmacogenetics International Consortium. So when we did the first 6,000, we were at 85% of the participants had one gene-drug pair or more. I can tell you that we've just finished 56,000 genomes, and 100% of us probably in this room have a gene-drug interaction in our genome, which if we come across the medicine, it will either not work very well or may work less well, or it could cause us harm. And so next year, the NHS is bringing live pharmacogenomic reporting, both from whole genomes, and where appropriate, there will be a panel test for clinicians in hospitals across England to apply to test suspected adverse reactions. This is important because 6.5% of patients have are admitted to hospital for an adverse reaction. That's almost over £1 billion of annual NHS spend. Only a proportion will be due to genes and drugs, but what if we could eliminate that? What if in the future, I don't see it immediately, but what if you could carry around in a device like this your own pharmacogenomic profile, and when I go to prescribe you medicine, wait a minute, doc, just check my genome, and you type in phenytoin, and it says, sorry, doc, no can do. It's red on the app, and you use a traffic light system, or amber means reduce the dose or adjust the dose, and green means there's no pharmacogenomic interaction. For those of you who are clinical pharmacologists like Donald, myself, and Bernard, that doesn't mean you won't get an adverse reaction. So we also assembled a coalition of researchers to work on these data, and this is the number that have volunteered from 413 institutions. We've just added South Africa in the last week. Very pleased about that, because there was nothing in the African subcontinent. Bit disappointed about South America, and this is a work in progress here. And they've won £24 million in grant. They have a 43% grant success rate, which, frankly, I've never had, so I'm actually very pleased for them. And 130 companies work with us on the data. I'll show you the data that they have access to very briefly, but it's 2.6 billion clinical data points. So we've now brought live a new National Genomic Medicine Service. This was owned by the NHS, and this is the work of us with my friend Sue Hill, the Chief Scientific Officer for the NHS, and her genomic medicine centres will become Genomic Services Alliances. There's a 7-lab hub network already. We will concentrate the entire knowledge base of genomics in the NHS, so every genomic test will go in a single knowledge base, and every patient will be offered consent for a search, and that will include longitudinal life course follow-up, recall for research, international researchers and industry having access from a secure data centre. Well, and everybody's data will be available for NHS care, and those that consent will be made available for research. We will continue to be the whole genome sequencing provider and the clinical interpretation pipeline, and work with industry and academia. To do this, my team and I looked with the NHS at 300,000 tests, upgraded 25% to new technologies, and over the next 5 years, starting on the 1st of April, the NHS will sequence 500,000 whole genomes. So this is now available in NHS care. And for the first time, we have geographic equity of access using this test directory, and these are the indications for whole genomes. It's on the web, you can look it up. This will gradually be iterated because we built into this commission service unusually, got them to build in an annual test review because this is such a dynamic area, it's changing all the time. But it does mean that we'll be able to bring the latest evidence to bear when we're sure it's right to do so in clinical care. To do this, we've had to build a national genomic informatics system. It's not live, it's in testing. We've had some challenges with that. As anyone who's ever done IT in the NHS will know, it's always a difficult thing. And this means you don't really have to know very much about genomics to order a test. You simply plug in the condition. It will tell you the tests that are on the test directory and that will be reimbursed. You can then look up the patient on the single NHS spine. It will then transfer the data from the spine into the record. And eventually, we're hoping it will take data, should it be there, from electronic records. So you'll have to do very little in the way of population. Draws family trees for you. You just have to tell it what the family orientation is, and it just draws it all for you and then maps it onto the people. And this then carries the clinical data through so that we can analyze the genome, and built in the system is a bioinformatics analytics pipeline, and that generates a report that comes out the back end back to the lab hubs for validation and then to the clinical team. Now, we're also working internationally with these countries, and we're looking at these types of other technologies because the genome in itself may not be the complete answer. It's maybe part of the picture. Now, to do this, we needed to support the workforce, and so what we did was spend £25 million on doing all of this training, and there's another aliquot of money being inserted at the moment to try and mainstream this as much as possible. Like many things we do in medicine, the success of this relies not on the province of a small speciality, but in how well we transfer this across our workforce so they feel comfortable in using it. It's not about knowing every detail of every single disease or every single gene association, but it is about knowing when genomics could possibly help you in the clinic. So in the future, we've been given a new mission by our current Secretary of State, and that will focus on about 1 million whole genomes. There'll be 500,000 done through the NHS service. There'll be 500,000 through Biobank. There'll probably be another up to 1.5 million tests. And then there's also this accelerating detection of disease cohort, which will eventually grow to 5 million. I'll just show you the pillars very finally that we'll be working on. We took advice from academics, the NHS and industry, and we'll continue to work on inherited and rare disease, expanding into rarer diseases which may have a slightly more complicated etiology, a few genes with variants with big effects. We'll continue to apply genomes alongside clinical trials in cancer, and we have a potential, under consideration, a potential program which will have societal and ethical research at the heart of it before, during and after, looking at comparing the Guthrie spot test of 9 things that we measure today in the first week of life with a whole genome. And it turns out we've just concluded a significant exercise that 1 in 260 live births harbour something in their genome that will be fully penetrant by their 5th birthday, and that there is an intervention. And only 8% of those interventions are expensive. And then finally, we'll continue to work on pharmacogenomics, most particularly applying genomes actually in this instance to work out who should receive medicines, stratified healthcare. Many people do not respond to the medicines we're giving them. Let's ask the question, can genomics, it won't work for everybody, maybe 1 in 10, maybe 1 in 20, but what if we can work out which expensive drugs can be applied most effectively? So we've also conducted, and one of the features of this program, we had a 35-strong participant panel. One of the features has been at the heart of this. We also went out to the public and patients, and they described the anatomy of the NHS social contract in terms of reciprocity, altruism, and solidarity. But they also gave us some red lines. They are not very keen on gene editing. They're not keen on that. We need to explain that if we're going to do it, and we need to be really careful about this because they were very worried about that. They do not want, if there's commercial uses for healthcare, they're okay with it as long as there's a fair return to the NHS. They do not want their data used for marketing in healthcare, and they do not want companies to have access if they do not make a fair return to the NHS. But they're happy for companies to work on the data as long as there is a benefit and upside to the NHS. They do not want these data used for a surveillance society, either for forensic purposes or for other legal purposes. And that's, by the way, on the list of unacceptable uses. And they also don't want this used for insurance, but in the United Kingdom we have a moratorium on the use of these data. So, ladies and gentlemen, I've kept you long enough. and I know there's some fluid balance awaiting you. So in 2019, you've earned it, having sat through this, the National Health Service in England has an equitable access for 55 million people, and I should say Scotland, Northern Ireland and Wales are also in the programme. I'm made sure of that. Standardised with a single 2 sides of A4 patient choice to have a test, and on the back of that the opportunity to consent for research, 2 sides of A4. Standardised throughout England and an approved national test directory, and we're going to build a single UK knowledge base to allow accelerated diagnosis for patients in the future and improve cancer care. De-identified where they consent for academic research and industry access, and an ambition for 5 million tests. But to emphasise a point made very eloquently by Paul, the world is a small place really, and we are world leaders for the first time in this area. We are actually doing something no one else is doing, and we're way ahead. But the duty here is for us to do this on behalf of humanity and with the rest of humanity, and the success of this will rely on a global coalition of intellects and not just the United Kingdom. So it's been a pleasure to be here. I'd like you to see the participants. They'd like you to see them. Many of these people have no diagnosis yet, but they're hoping that you're one of that 3,580 researchers who are working on their data, and that's why they've given permission for you to do so, to make sure they do get an answer in the end. And then I'd like to thank the teams that have worked on this across this nation and overseas, and also our principal funder, the National Institute for Health Research. And finally, should you wish to know more, you're probably feeling anaesthetised, but if you're not, do get in touch. Thank you so much for having me.